Hey folks, Ms. Gosling here. In this video, you're going to learn about power. By the end of the video, you'll be able to define power and solve problems involving power. So let's go ahead and get started. So first of all, what is power? Well, I can tell you what it's not, and power is not. We're not talking about political power or military power or any other kind of power that you might be used to. Instead, what we're talking about is your ability to do work quickly. So we define power, which we use the capital letter P to represent, and that which we measure in watts, which we use a capital W to represent. And I know this is confusing because work is a capital W and measured in joules, and power is a capital P and measured in W. But in the grand scheme of things, it could be a lot more confusing. So just remember, we're going to use the unit W to represent power. We're going to use anything with the unit J for joules represents work. And our power is going to be equal to our work, which we represent with the letter W and measure again in joules, divided by the time taken to do that work. So time, which we're going to measure in seconds. So let's go ahead and look at some example problems. You lift a 5-kilogram box up 100 meters in 1 minute. How much power did you output? So let's draw a picture. Here's my 5-kilogram box. It's going to go through a 100-meter displacement, and my time taken is 1 minute, or 60 seconds, since there are 60 seconds in a minute. Now that I have a picture, I'm ready to list out my givens. So I know that the mass of the box M is 5 kilograms, and I know that I'm lifting it up, so the force that's acting on my box is mg, or 5 times 9.8. Or, if I really want to write this out, 49 newtons. I also know that the displacement of my box is 100 meters, and that the time taken for me to lift my box is 1 minute, or more importantly, 60 seconds, since remember, we want to keep things in our standard units. I also know that my unknown is the power required to lift the box up. So that means that the equation I'm going to use to solve this problem is power equals work over time, or expanding things out, power is equal to force times displacement divided by time. Now that I have that equation with only my knowns and unknowns, I can go ahead and sub and solve. So my power is equal to my force, which is 49 newtons, times my displacement of 100 meters, divided by 60 seconds. Thus, the power required to lift my box up is 82 watts. And you can see that capital W for watts is my unit for power. Let's look at another example. Jim merges onto the highway, doubling his velocity. This car has a mass of 1,500 kilograms. His initial velocity is 10 meters per second, and it takes him 1.5 seconds to accelerate. How much power did his car output? So we have Jim driving down the highway, and he is going to have an initial mass of 1,500 kilograms and an initial velocity of 10 meters per second. Then, 1.5 seconds later, he'll be traveling, again, he'll still have a mass of 1,500 kilograms, because the mass of the car is hopefully not changing, but his velocity will have doubled to 20 meters per second. So let's go ahead and list out our givens in a nice, clean order now that I've drawn a nice, messy picture. So I know that the mass of the car is 1,500 kilograms, that its initial velocity is 10 meters per second, and that its final velocity is 20 meters per second. I also know that this change in velocity occurs over a time of 1.5 seconds, which leads me to my unknown. And my unknown is, of course, the power output of Jim's car. So I know. So let's go ahead actually and draw our equation because that part is actually pretty straightforward, right? We know that our equation is that power is equal to work over time. But for this question, we can't use work equals force times displacement. So we know again, work equals force times displacement. But we also know work is equal to my change in energy. And in this case, I don't know anything about forces or displacements. But I do know about how the kinetic energy of Jim's car is changing because he's speeding up in this problem. So that means I'm going to write my power is equal to my change in energy over time. I'm going to go ahead and expand the top of that fraction out. So my numerator becomes, so my change in energy is going to be my final kinetic energy minus my initial kinetic energy over my time, because the height of Jim's car is not changing, right? He's traveling horizontally across the highway and speeding up. Expanding this out one step further, I know that 1/2 times my final velocity squared times my mass minus 1/2 times mass times my initial velocity squared is going to be a better way to write my numerator because my masses and my velocities are what I know, not my kinetic energy. I'm going to divide that all by time. And now that I have this written out, I am ready to sub and solve. So power is equal to 1/2 times my mass of 1,500 kilograms times my final velocity squared minus 1/2 times my mass times my initial velocity squared, all divided by my time. Now, once you plug this into your calculator, what you'll get is that your power is 150,000 watts. And there you have it. In this problem, we have successfully used the work energy theorem to solve for power instead of using the definition of work to solve for power. As you can see, depending on what information you have, you can choose either method. So let's go ahead and talk takeaways. So first of all, power measures how quickly work is done. And we can use the equation power equals work over time to calculate power. And we can use two different ways to calculate work. We can use work equals force times displacement, or work is equal to our change in energy, depending on what other information we have. So with that, you now know how to solve power problems. Give it a try on your own. Best of luck and happy solving.